So the next section for the transformer tool, we try to go into more practical way to understand transformer. So in here, we show you, say, the auto transformer, a new type of transformer. That's also really interesting. We will show you how to calculate losses and impedance, and most high-frequency transformer, and the different kind of transformer connection, three-phase transformer, single-phase transformer, give you more understanding of the practical transformer. And then, firstly, ask a simple question. Do you know what's meaning for auto transformer? Do you think this a transformer can be automatic, or why we have terminology called auto transformer? Anybody can give me a hand? Auto transformer? What do you think? Auto transformer.
It's the things in the movies.
No, not that transformer. Robotic transformer. The robotic transformer in the movie is autonomous. But in here we call them electrical winding transformer, right? I'll show you later on. Yeah. But transformer movie is nice. I mean, I don't know why they use the term called transformer. And they transform. Because they can transform, right? And I myself building a new project is configurable electric vehicle and configurable robot. So that means in the future, for the robot, the vehicle are configurable. That's like the movie transformer. So that's to say in the future, robotic systems, as I mentioned to you, we got multiple motors that plug in and the battery everywhere. We don't like single battery on a robot, because once you change the change the another outlook, the battery don't know where to put the battery. But if you have each good battery on all the arm, limbs, skull, then you can able the multiple energy supply to each of the motion system. So that's how we configure the robot, configurable robot, or configurable vehicles. So that's how we see the future for robotic systems. But anyway, come back to here. And so besides the voltage and current conversion for transformer, what else we can produce for transformer? How do we connect a number of transformers together? So you're given one transformer, but sometimes we find the voltage and current not sufficient. You may need to connect a few together. Just like a battery, one battery 1.5, four battery 1.5, adding together become 3 volts. But in transformer, this is 120, this 120, when put them together, can it go for 240? How to connect them? The current, the current is one end, putting them in parallel, and we get 2M transformer. That's the question we like to answer. So that's the way how we're able to put in number of components together. Let's see what we have here. So, and for content for today, we're going to understand more about matching transformer. Transformer can be used as a metric to match the impedance. We can also look into the transformer connection, how to connect various transformers together. We're also looking into auto transformer, a kind of the commercial transformer. And three-phase transformer is also really important. How to connect three-phase voltage in the transformer. And nowadays, most of transformer are three-phase, only small power and single phase. And then transformer losses, how to really calculate losses like the component we mentioned to you just now. So that's another important topic we like to look into. So transformer matching. So like the transformer, we call term ratio N here. So the voltage, we have this relationship. The current, we have that relationship. So if a transformer, the output connect to impedance Z here, then of course, the input impedance we can see in here must be equal to input voltage over the input current. That's the impedance Zx. For the second side, we got the Z in here. So this impedance must equal to E2 voltage divided by its current. Then if we putting these two equations together, then we can build a new equation. That means the primary side impedance and second side impedance are related to N squared. So that is to say, if we have impedance here, I want to change the impedance to another impedance, I can use transformer term ratio to adjust this impedance. For instance, if the output is a resistor or inductor, I want to change its impedance. I can use transformer to do that. Very common application will be the speaker. Some speaker, 4 ohm, 8 ohm, 16 ohm, if you want to change the impedance of the speaker, especially you like to have a more perfect audio sound or impedance matching to reduce the standing wave between them, then you may need to use transformer matching. Many of wiring connections have a perfect matching of the impedance. I think quality and efficiency will be better. So that's why a transformer, one of the major applications for transformer will be the matching. Using this resistance putting here, then we're able to get impedance matching, only calibration of the end. So that's one of the interesting application. Have you seen that? Have you made use of the transformer matching to regulate the transformer impedance? So for instance, we can make use of this correlation to understand more about how we use it. For instance, we got transformer T in here, N1, N2. The primary side, we have 5 ohm impedance, and the input is 10 volt. In the secondary side, we got a 20K. This is a capacity, right? But anyway, I use impedance to represent them. I also 40K ohm of resistance. So we assume voltage across it equal to E. So for that kind of circuitry, we can use the impedance matching equation to make our calculation simple. So we are asked to calculate the primary side current. What's the current in here? You see, we cannot just calculate it because it relates to a transformer. We need to know all this voltage. If we know this voltage, then we can therefore calculate this current. If we know this current, then we can know this current. But we're not quite sure about this voltage yet, because this voltage are related to how these 3 components share the voltage. But we also a transformer here. So we're not quite sure how they share the voltage. Theoretically, you need to know this voltage. Not only this voltage, if you know the circuit theory, then you know that you need to know this voltage and also need to know this phase angle. So that means if you don't use the impedance matching, the calculation for the current will be quite complicated. So now that we make use of the transformer turns phasor matching, we can convert this circuitry into this one. Because we know the transformer turns ratio is 1 to 100, then the impedance C, we can therefore change it. 1 to 100, then we can therefore reduce to 2 ohm by have an n square relationship divided by 100. Oh, there's a typo error here. There should be 20 anyway. Yeah. So that will become 2 ohm. That's the typo error here. And then 40K in here, then we multiply by n squared. That become 4 ohm. So now then the whole circuitry, we can therefore become a new series circuitry in here, right? So now then we got new series circuitry here, much easier for us to estimate the current. The input voltage is still 10 volt, and the impedance will be this field parameter. Then we can just get the total impedance of the circuitry. So again, one is capacitive, one is inductive. Then we can get the new, so become total impedance 5 ohm. So the current, we can use primary side voltage divided by its impedance become 2M. So that means this current, because we refer everything to the primary side. So now then we can, this current will just equal to the primary side current, 2M. Then the secondary side current, we can use the transformer relationship from the 2M, we can get the secondary side current, then become 0.02 M, just a simple relationship. Then once now we know this current, then to get the voltage across the 40K ohm, this current multiplied by this impedance, then will just give us 800 volt of voltage. So this method, you can see that we don't need to care too much about the phase angle, secondary side voltage. So complicated. Before, if you don't know the impedance matching, because you have 10 volt here, after this impedance, this voltage is not usually zero phase angle, some phase angle. And this voltage potential divided by these three components. So not an easy way to get this voltage anyway. But now then you can use the impedance matching with everything to a single loop of the circuitry. Then you get this current easily. Once you get the primary side current, you can refer to the secondary side. You can therefore get this voltage. Quite straightforward. So this method shows you how we use transformer impedance matching. The application of here will be usually using this matching method. You can make the calculation simple, easier to manipulate. And then you can also calculate the either side in separate manner. Any question? Since you have learned this concept in the past, since you all have no question, right? Or this is too simple. I think this all simple, really simple concept. You don't have any equation. Basic Ohm's law in here, A squared equations, right? Transform equation you all know. So that's why this topic is quite kind of simple topic for you to start. So next is about transformer connection. Now, just now we mentioned about dot location. So now getting some interesting. How we connect a number of transformer in parallel series connections. Why we need to do that? Because sometimes we would like to do various components to connect in the transformer system to vary the power level. For instance, one transformer is 1 kilowatt, this transformer is 1 kW. Putting two together in theory, we can have 2 kW of power. But how is the voltage current look like? So now that you see, if you try to connect two transformers in parallel in such a way, you see when we connect transformer in parallel, then we need to take care about this dot rotation, dot here. That means these two are in same polarity. When we connect these two transformers together, these two must be in same polarity. So if you want to parallel, we need to connect all the dot in this way together, parallel, these two in parallel. So now then, these two transformers are connected in parallel. And then, without looking at here, of course, I showed you that. Then the transformer turns ratio, when two transformers connect in such a way, the turns ratio will still equal to the voltage ratio, right? Because, but bear in mind, in here will be, we assume the two transformers are the same or identical. So that's why we're able to connect them in parallel. But in theory, no transformer can identical. So that means although we parallel the voltage, but the current may not able to share equally unless they are perfect identical transform. Yes.
What would have happened if they're not aligned in the same way?
Then short circuit. You can see that one of the problems I may ask you will be, if this stop putting in here, what happened?
I go through one.
You shorting out two polarity together, right? In second side, on fire and go up probably. Then we confuse. Right. Just like you're putting two batteries short circuit, right? 1.5, 1.5, inverse polar on short circuit. Same as this, right? Okay. So that's a dot rotation and important. I think in tutorial or maybe in the quiz or midterm, I expect a number of this connection to see yes or no, or how is the power. So the short circuit, with the voltage being enhanced or short circuit. Yeah, that's a quite interesting connection. So in theory, you see if you got current in here, if they are identical transformer, if the current is I, then this current should equal to I over 2, and this current should equal to I over 2, right? If they're identical, but nothing can be identical. So this two current will share in separate way. They may delay a little bit. So that's why I say here, no two transformers can be identical. So they may not able to share their power
and current equally. But for theoretical study, if they actually equal, you can therefore share the current equally. We're shortening the voltage, so the voltage might be the same anyway. But if they're not equal, there may be some current pass through internally somewhere. You damage the performance. Yes?
So this is only useful in theory.
No, many people still do that. You see, if you go out to buy two same transformer, if you don't have any other choice, you want to double the power rating, you can still pair it. As long as you make sure the dot rotation is connected properly. But as I mentioned before, if they are equal transformer, they will share the current equally. But if they're not exactly equal, probably this one may be 55%, this one will be 45%. And then there will be a bit of current circling internal on some internal one, which we don't quite like. So this is not a good connection. It's only kind of the last solution when you want to connect the power. We got many other connection methods which are much safer, much better than this. So this is not really good. Method. So I got some name here. So I say this one is PP, parallel, primary side parallel, and secondary side parallel. And then another way will be if we parallel the primary side, series second side, then even though two transformers is perfectly identical, we're still able to work quite properly. And then you see here the voltage conversion ratio, just using this method. Output voltage is equal to 2 connected in series. So that means this is the top transformer voltage conversion, this top transformer connection, because we're putting 2 dots in here. So this 2 dots mean they're connected in series. We don't try to short circuit in the secondary side. So these two are connected in series, like this, adding this one. So simplify them will be twice, double the turns ratio. So this way, we can make a transformer can double its voltage conversion without circulating current. Because even though the two transformers is not identical, they can still do a good job. Yes?
Would this just be increase in voltage or a decrease in current?
You can see that the primary side, we shorten out the voltage, the equal voltage on the primary side. The second side, we look at double the voltage, increase the voltage by putting these two in series in this manner, right? So the power rating is already double. Output voltage is already double. Yes.
Is this like kind of a basic design for a voltage amplifier?
Can be used as amplifier. For instance, if we want to use two transformers to double the output voltage in some connection. For instance, if you only have 1-to-1 transformer, 120 volt to 120. But now then, your boss asked you to design transformer, output voltage will be 240. You can't do anything. You can use this method to double the output side voltage. Or of course you can redo the winding, but that will be inconvenient, impossible. Yeah. But that simple method, how you double the voltage. How we do that? Make sure the dot location will be properly located. So that's not the topic here, quite funny topic, how to manipulate the connection parallel series, right? But next lecture we'll go through more connection. Now we go through P to P and P to S. Next lecture we'll go through a few more. Okay, see you in the lab or see you on Wednesday.
What?